Hi everyone, I am Shomodit Chakraborty, a third year graduate student at Vanderbilt University. Today I am going to discuss about the paper called Using Mobile Augmented Reality for Spatial Cognition. In today's era, we can develop augmented reality applications on various AR head-mounted displays such as the Microsoft HoloLens or the Z Mini, as well as on our regular mobile devices such as iPhones, iPads, or various Android devices because of their adequate hardware capability to run AR apps. However, if you go through the AR literature in general, you will find that most of the studies have been conducted using AR HMDs. In our study, we mainly focused on the mobile AR displays and we ran a distance estimation study and two affordance judgment studies using these devices. There are some benefits of using them in several experiments. So, what are some of the benefits of using mobile AR displays for running experiments? First, we can run partially controlled studies in the wild. People can easily install an app on their mobile devices, run the experiment, and send the data back to us very easily without even coming to the lab physically to take part in the experiment. Now, why partially controlled? This is because we never know in which environment the user will run the experiment. But using various instructions, tutorials, and graphical user interfaces, we can guide him or her to run an experiment in a specific way. That's how we can run a partially controlled study in a distributed environment, which would be helpful to run experiments during a pandemic like what we are facing now. Second, we can recruit people not only from a group of university students or friends of the researchers, but also we can recruit people from all over the world by sharing the apps with them very easily. Here comes the next question, and that is, what are the motivations of our studies? First, whether the addition of ARQs to the real environment can improve people's spatial perception using mobile AR displays. And second, what can be the challenges and limitations of using mobile AR displays while running such an experiment in uncontrolled distributed environments? To check that, we built three different mobile phone apps for conducting three different experiments. Because of the pandemic, we were unable to run this study in our lab, and that's why we distributed these apps via the Google Play Store and the Apple App Store so that people could easily install and run them in their devices. At the end of the experiments, these apps automatically send the data back to us via email. So let's talk about an overview of experiment 1, which consists of two parts. In the first study, we tested people's abilities to judge whether they could pass through a virtual aperture seen through a mobile AR display without an ARQ or the pre-Q block with an ARQ which will represent the shoulder width of the participants, and again without an ARQ or the post-Q block to check whether the ARQ helped them to judge the minimum possible distance through the aperture correctly or not. By pressing either the outward button or the inward button to move the virtual poles, move apart from them or move closer to them, participants were asked to adjust the aperture to the smallest so that they can pass through without turning their shoulders. When they are satisfied with the distance between the poles, they can hit the blue button to register their estimated smallest possible distance through the aperture. The experiment included two ascending trials where the poles started at 70% of shoulder width and two descending trials where the poles started at 180% of the shoulder width. All these four trials were tested for all the three conditions, that is the pre-Q block condition with the ARQ condition and the post-Q block condition. We recruited 26 participants in this experiment from USA, Europe, and Asia, where 12 of them were females and 14 of them were males of age range 19 to 68 years. We ran a repeated measures ANOVA on the ratio of estimated aperture width to actual shoulder width, comparing three blocks, that is the pre-Q block, ARQ block, and the post-Q block. If the ratio became 1, that means that the estimated aperture was equal to the actual shoulder width. We found a significant effect of the block. We showed that the judgment in the post-Q block became closer to the shoulder width compared to the judgments in the pre-Q block. This means that the ARQ reduced estimates for passing through when the Q was removed, showing improvement in users' action judgments in the post-Q trials by training them with an ARQ. Now, let's talk about an overview of the second part of the experiment 1, where we tested people's abilities to judge whether they could step over a virtual gap seen through a mobile AR display without an ARQ, or the pre-Q block with an ARQ, which will represent the step size of the participants, and again without an ARQ or the post-Q block to check whether the ARQ helped them to judge the maximum possible distance over the virtual gap correctly or not. By pressing either the narrow button or the widen button to make the virtual gap narrower or wider, participants were asked to adjust the gap size to the maximum that they can cross in one step. They can register the maximum step length by hitting the blue button. Here also, we used 12 trials over the three blocks, that is the pre-Q, ARQ, and the post-Q blocks in this experiment, like the first part of experiment 1. We recruited 26 participants in this experiment from USA, Europe, and Asia, where 13 of them were females and 13 of them were males of age range 19 to 68 years. 3 participants were excluded because of inaccurate measurements. We ran a repeated measures ANOVA on the ratio of estimated gap size to actual step size, comparing 3 blocks, that is a pre-Q block, ARQ block, and the post-Q block. If the ratio became 1, that meant that the estimated gap size was equal to the actual step size. We found that the judgments with the Q block were greater than the judgments in the pre-Q block trials. However, we found no difference between the judgments in the post-Q block and the pre-Q block, which suggests even if the ARQ increased estimations, the effect of the Q did not generalize when the Q was no longer present. So these two experiments were part of the experiment 1. Now let's talk about a little bit of the experiment 2. In this experiment, we evaluated how social cues affected egocentric distance judgments of a standing avatar or a coughing avatar with either masked on or unmasked seen through a mobile AR display. The avatars were placed at either 4 feet or 8 feet or 12 feet randomly, and the people were asked to register their estimated egocentric distances of the avatars using the graphical user interface of the app. We recruited 38 participants from USA, Europe, and Asia to run this experiment, among whom 6 participants' data were discarded because of faulty data. So, among the left 32 participants, there were 14 females and 18 males of age range 19 to 69 years. We ran a 2x2x3 repeated measures ANOVA on the mean distance estimations, and we found that the estimates were quite accurate with respect to the real distances, which is represented by the black dotted lines, without having any effect of the coughing animation or the mask and unmask conditions. We ran a 4 by 3 by 2 repeated measures ANOVA on the ratings of comfortability of how comfortable people felt around each avatar condition in each trial based on a 5-point Likert scale where 1 means very uncomfortable and 5 means very comfortable. We made the mask static avatar as the control as we thought that this avatar condition will seemingly be the most comfortable choice by the people among the other three avatar conditions, and we found that the unmasked coughing avatar got lower ratings compared to the mask static avatar. There was no difference between the other two conditions, that is, the unmasked static avatar and the masked coughing avatar, which suggests that people felt comfortable around the masked static avatar in general. And finally, the level of comfortability increased with the increment of distance for all the animation conditions. So, what can we take away from the studies? First, people underestimated their capabilities for judging affordances, but accuracy increased after training with AR cues in experiment 1. Second, distance estimates were accurate with no effects of mask or coughing in experiment 2. Overall, it can be said that AR cues can improve accuracy of spatial perception using mobile AR displays, but the effect may not be generalized always. Also, we have seen that it is possible to run control AR perception and action studies in the wild using mobile AR displays. So, what are some of the challenges that we faced while running the experiments? One of the biggest challenges we faced during running the experiments in a remote way was how to let the participants understand what they need to do throughout the experiments. So we develop clear and easy to understand instructions at the beginning of the experiments along with some practice trials. For example, we showed them how can they measure their shoulder width or the stride length, or how can they scan the ground to run the experiments. Some of the other challenges that we faced were how to deal with the internet that the participants used so that we could get the data back to us reliably. Also, Apple did not allow us to release the distance estimation app on the App Store publicly because of some security concerns. So we had to send the beta version of the app to the participants via email. And there were some other challenges as well, but for the sake of the time, I'm skipping them for now. Some suggestions to run a remote study like this will be: first, clear instructions with images or videos are critical to let the participants understand what they need to do in the experiment. Second, email services or Google Form along with Google Sheet can be a reliable choice for data collection, assuming that the internet connection of the user is stable enough. In conclusion, it can be said that mobile AR displays can be used to conduct remote experiments to assess spatial perception. However, to achieve this goal, researchers must pay close attention to the clarity of experimental instructions, and they need to ensure that the data sending mechanisms are reliable. I would like to thank our sponsors and my co-authors for their continuous support throughout this study. I would like to thank you for listening to my talk, and I am happy to take questions now. Lastly, if you want to try the apps in your phone, you can scan these QR codes to install them in your device. Experiment 1 has the Android versions available, but iOS versions are not available because of Apple's policy. However, Experiment 2 has both versions available. Thank you and enjoy running the experiments.